Hello and welcome to Reigate Further Maths video on oblique collisions and a vector method for finding the unknown line of centres. So unless a question states that the line of centres is parallel to I or J, it can't be assumed that that's the case. If the line of centres is given, so for instance, you're given an equation of the line or you're told that it's parallel to a particular vector, then we can use methods that we've done in the last few questions. But if we're not given the line of centres, we need to find it. So we're going to do that by finding conservation of momentum to find any unknown velocities. And we're going to calculate the impulse on one of the particles and use that to find the line of centres. Let's do an example and it will become clear how you will use this approach. So we've got two small spheres, A and B, equal radii. The mass of the first one is 2m and the second one is 3m. They're moving on a smooth horizontal plane and they collide. We've got the velocity of A before and the velocity of B is that, and afterwards we've got another velocity there. So momentum is conserved. So we're going to use the principle of conservation of momentum. And I've got 2m multiplied by 0.5 plus 3m multiplied by 3 minus 1 is 2m multiplied by 3,2 plus 3m multiplied by xy. So I've just used the principle of conservation of momentum to write an equation. So let's look at the I component here. I've got 9m must be equal to 6m plus 3mx. So that gives me that x is 1. And in the j direction, I've got 10m minus 3m is 4m plus 3ym. 7m here, so take that 3. So I get y is equal to 1. So I now know this velocity here. I want to find the direction of the impulse. So I'm going to consider A, and I'm going to use impulse equals change in momentum. So impulse is equal to the momentum at the end, which is 2m32, take away 2m times 0.5, which is 2m times 3 minus 3. This is the direction of the impulse. I could have used particle B to find the impulse, but because we worked out that velocity there, it's better to use particle A because we were given both of those. So, working through this, we know that this is the direction of the impulse. So the impulse acts in the direction. Now I could write down 3 minus 3, but that is actually, I can divide by 3 and have that as being 1 minus 1. So I've now got the impulse direction, which is 1 minus 1. So the impulse direction is like this. And that means the spheres collide, something like that. What I want to do now is find the component of each particle parallel to the impulse. So for A, beforehand, so before, put up here, component parallel to the impulse. So for A, before, we've got 0.5. And if I want to find the component in the parallel direction, parallel to this 1 minus 1, remember that you use the dot product, and you will see textbooks and worked examples using the unit vector for this. That's not necessary because it will cancel out. So I'll show you that they'll cancel. So this little bit here, we don't actually have to have that in. And that is equal to -5 over √2. So that's the component of A before. We now need to have a look at the component of B before. So the component of B before is going to be 3 minus 1 dot 1 minus 1 times 1 over √2, and that gives you 4 over √2. The reason we're doing this is we're going to use in a moment E is separation over approach. And this is the approach velocity, these two terms added together, because we've now got them in the direction of the impulse. So we need to find A before and B before. And then we need to find A afterwards. So A afterwards, again, we're finding the component parallel to the impulse. That's going to be 3, 2, dot 1 minus 1, again, multiplied by √2, which gives me 1 over √2, because I've got 3, take away 2 there. And B afterwards is going to be 3 minus, oh, wait a minute, we had to find B afterwards, so we had it up there, apologies. So that's going to be 1, 1, dot 1 minus 1 times 1 over √2. And when we work that out, we get 0. So we've now got everything we need to use Newton's law of restitution, which is that E, which we're trying to work out, is separation. Now, the separation speed is this velocity minus this. So that's 1 over √2 divided by the approach speed. Now, the approach speed, we've got this minus this velocity here. That gives me altogether 9 over √2. So this is equal to 1 over 9. And that is the value for E we get. So what we've done here is we've found the component of this particle parallel to the impulse direction. We found the component of this one parallel to the impulse direction, and that gives me my approach velocity. Then we've looked at what's happening afterwards in that direction using the same components, and then we have divided to find E. So you just have to be clear in your head what you're doing with this, and then it will work out quite nicely.